This is the second lecture of today's session and last lecture of Professor Dario Politi in this numerical methods of quantum many-body systems. And over to you now.
Thank you, thank you. Hi, can you hear me well? Good? Okay, I would like to, first of all, address some of the questions that were asked to me after the last session regarding neural quantum states, neural net quantum states. One question was, what reference can you check, right? What kind of literature to quickly jump in, okay, after these lectures in case you want to know more, or and let me suggest three. I mean, there is a few. Let me suggest three. First of all, I think most important, you should read the first paper by Carleo and Troyer, Science 2017. That is fundamental. It is also actually very clear. So, 2017. Okay, so this is for sure. Although it's not a review, I think it's a very good start. There is both ground state search and time evolution, so that is a good way to go. Another review paper, there have been a number of review papers that look at machine learning in general and quantum physics. Okay, and then they contain also those kind of studies where you use machine learning to detect different phases of matter, these kind of things, right? Which is also very interesting, but it's not really neural net to quantum states. So I will not tell you about those. I will tell you another one by Lang and others, like Annabelle Bord and so on, and et al. And this is was in the archive in February 2024. It's easy to find. It's about all the architectures and different things. So it's very nice, good read. And then another one that was done last year by Schmidt and Heil, 2025, on the archive. This one I don't think is published yet, and it's on time evolution mostly. This is focused on time evolution. And in fact, back in 2020, they had a very nice PRL where they used convolutional neural networks to do some time evolution. There was a very nice paper. And there were other papers around that time by Gutierrez, Mender, okay. So if you want to read something, there is also some very old lecture notes that Giuseppe Carleo gave in a school when he taught at a school in Beijing. So if you search for Carleo review, neural quantum states, Beijing, or something like this, summer school, then you will find also that PDF. It's quite small, concise, mostly on RBM, but it's also very, very insightful. So I can also strongly recommend that those notes. Okay. Good. Okay, so this was one question. Any other pressing questions from my, okay, so one big problem, and maybe that I took for granted and I didn't describe well enough, is what do you mean when you go from sum of x of p of x e loco of x to one of a number of samples, sum over the different samples, okay, of E log of these samples, okay? What did you do? How you done it? How do you sample from the probability distribution, okay? And this is actually a very important question, and maybe I will spend a bit of time today to talk to you about this. Then I will try to go back to the ground state search and talk about stochastic reconfigurations, and then try to go to time evolution, and then hopefully we'll finish. Okay. There are so many other things that we could talk about, but I will try to stick to these key aspects. Okay, so how do you go from here to here? And in particular, the point is that your neural network gives you something some psi, theta, or some configuration, which is actually not normalized. Okay? But what you can do, to sample from this, one thing that you can use is a Metropolis Hastings algorithm. Metropolis Hastings. And how does it work? For given a certain configuration, you build a Markov chain where you propose another configuration through some function g. Given x, you propose x prime, okay? And then you see whether to accept it or not. Okay? If you accept the configuration, okay, let's say you have xn, I go to x prime. If you accept the configuration, yes, then you have your new configuration xn plus 1 is equal to x prime. Okay? And if you say it's no, then you go back and you reproduce another configuration. Okay? Now, to do this, you need two things. One is this function here that proposes a new configuration. Okay? And this has to be the property that it needs to be aperiodic and positive recurrent, which means that it's able to, in a finite number of steps, to cover all the points. Okay? But there is no regular patterns in it. Okay? And then you need to accept it. And to accept it, if you are able to enforce a detailed balance, okay, then you're sure that you have a unique distribution you attend to when you do these procedures. Okay, and so the acceptance is what you would like to do is you draw a random number from uniform distribution between 0 and 1, and then you compare this random number R with you should be the probability of the new configuration divided by the probability of the old configuration. Okay? So this is what you compare. But you don't have this information. You don't have P. What you have is something proportional to P. And since it's proportional to P, let's call it F, the ratio is still the same, right? So the fact that we don't know what is the normalization doesn't matter because just we're looking at ratios. Okay? So you compare this R with this ratio, which you can get from the neural network, and if this is larger, sorry. F of x is the output of the f of x is psi modulo square. Then you get it from the network. Fair enough? Okay. So now you compare the two, and then if it is the probability is higher than R, then you accept. And if it's smaller, then you reject. Okay, and then you continue. So this is, maybe if time allows, probably most likely not. I think so. Since there is not enough time, I'm not going to prove this to you. But this is the approach. Okay, and in this way you can build up. But you need to be careful to two things. When you generate samples, the samples that you want to use, they need to be uncorrelated. So once you generate one, you need to maybe go through and accept it. You have to go through a few times, okay? This kind of, and until the correlations between the samples decay, and then you can accept it, okay? And for this, you need to maybe have an idea of how long the correlations are, how many steps you need to do for the correlations to decay, okay? But once you do this is very nice algorithm. One issue with this algorithm is that you, in certain scenarios, you may to reject many, many times, you can become very slow. And so there are, of course, other techniques to try to reduce this rejection rate. But once we talk about neural networks, we can also use a different type of neural network where we sample in a very different way. And these are called autoregressive. Okay, so autoregressive neural networks are such that the probability of a certain configuration x1, x2, xl is given by a function p of x1 times p of x2 knowing x1 times p of x3 knowing x2 and x1, etc., etc., until you have p of xl knowing x1 all the way until xl minus 1. Okay? So it's a specific ansatz that you use to represent your probability distribution. Okay? So in the sense, this is a bit less expressive, okay, than what you had before. But it has an advantage that you can sample configuration from this very, very quickly and very easily by doing this. First, you pick p of x1, and you compare it to, again, a random number, right? Okay. So you have, again, you have a p, and you have your r, and you compare. Okay, if p is larger than r, so then let's say you say p of up, okay, and let's say x1 for up is equal to x1 is equal to 1 for up, x1 is equal to minus 1 for down. Okay, so you say, okay, what is a p of x1? Okay, if p of x1 is larger than this random number that you picked, then you say, okay, then x1 is equal to 1 up. Okay, if it's lower, I know it's down. That's my first sample. Once you have your first sample, okay, then you compute, you put it back in the neural net, or you compute p of x2 knowing x1. And you do a similar scenario. Oh, what is a p of 2? Now that I know that x1 is up. Okay? And then you get the new sample. And then the new element of the sample. And then you continue. You have L steps. Every time you need to re-go through the network again and again. Okay, it works like this. You have your some black box network now, doesn't matter. Okay, I will describe well later how to do this network, because you need to have a specific mask inside the network to ensure that it's autoregressive. But anyway, so you put your x1. Actually, at the beginning, you just get the output. You look at this value here. Then once you know this value here, and the next step, you say, okay, so this is the value of x1. I want to know what is x2. Once I know x2, then I put inside here. I know what is x3. I know what is x2, sorry. I want to find out what is x3. And so on and so forth. Okay? All the outputs here can only depend on things before, cannot depend on things after. Otherwise, you lose this autoregressive property. That's where you lose a little bit of expressive power. Okay? Maybe a lot. But then you have this advantage that you don't reject. You just, every time, you get your samples. Okay? So this is quite a nice approach to sample. Throughout the calculations, though, yes?
You said that P of x is proportional to psi theta of x mod square.
P of x is proportional to?
Because psi theta are not normalized.
Yes. Haha. Okay, I wanted to discuss this. Maybe I'm going to answer your questions before you ask it. Okay. So, let me see. The output, though, in general, Okay, this works very well for classical neural networks. You look at classical problems, and you can put as the last output, you put a sigmoid function. Everything real, you put a sigmoid function, and the sigmoid function is like this. Okay, it's between 0 and 1. So whatever comes out, you can think of it as a probability. Okay, but now we are in a more general scenario. Okay, my outputs out of this thing here. These are the inputs, let's say. My outputs could be a complex number between, depending on the activation function of the last layer that I put there. So then, what do I do? Well, I know that the output can only be I know that I'm looking only for values 1 or -1, right? I can put two numbers here. Okay, then it gives me for +1 and for -1. Okay, so I can get, instead of one number, I can get two, for +1 and for -1. And so let's say I have a psi for +1 and a psi for -1. Okay, can I build a probability? Yes, of course. I do modulo square of this, I do modulo square of this. Okay, and then I know the probability of +1 is equal to modulo square of psi of +1 divided by modulo square of psi +1 plus modulo square of psi -1. Okay? And this is obviously between 0 and 1. Okay? Yes?
You said that the sigmoid function cannot be used because of the complex number, but why is the complex number comes into play? This is a, you converted into the probability, which is a...
No, you could have, okay. What I'm saying is that if you have a sigmoid function and you only have this one output, and you have, everything is real, it's very clear. Okay, but now we want to get psi or maybe the logarithm of psi there. Okay, and then I say, okay, well, I have this kind of outputs. How do I define the probability? Okay, I can look at the two outputs, two potential outputs, bring it together, and I can write the probability. And then I look at this number, I compare it to R, a random number that I picked. Okay, and then we know whether I can accept or not. Fair enough? Okay, cool. Okay, you can try. Yeah, another thing that you can do that is also quite common. It's called importance sampling. Importance sampling. So the idea here, instead of having to resample all the time, okay, I can, for a certain number of steps, not resample, but adjust, having a decent estimate of what the probability function is. And maybe one way to look at it, let's say if I want to compute the expectation value of some v of x, what I need to do is v of x times p of x in dx, right? Now, what I can do, I can multiply and divide by another probability distribution, okay? And now I will sample over this one, this quantity here, okay? So I'm looking now, instead of looking at the expectation value, let's say, over P of V, okay, I look at expectation value over Q or VP over Q. And so the way you can do this is, for example, you keep the sample from a previous optimization, okay? But now, after you have optimized, the parameters of the network are different, so P is different, okay? So you use, so then you update the values of P and Q, and you have the new weighted probability of this new configuration after you shifted, okay? Now it's interesting that once if you have a very clever choice of Q that is, same as VP, ideally, okay? Then the expectation value is of a constant has 0 variance. So if you do this also very carefully, and you can also reduce the variance. Okay, so this is another technique. And, we also come up with some other tricks to try to improve or to do samplings in different ways.
Can you explain this importance?
Yeah, sure. So you will be doing the part in white, right? Expectation value of U of x. But now you multiply and divide by another probability distribution Q of x. And instead of compute the expectation value over the distribution P of V, you do the expectation value of a distribution Q of VP over Q. It's the same thing. But now instead of, I don't need to sample from P that I will be doing here. I can use my sample from Q and evaluate this quantity here. Okay, and so you can do it for a while, and then you start to resample again. Okay, so there was a nice paper, I think for ground state search by Hanpu, Rice University, that did this quite a few years back, and of course maybe many people are already doing it in their codes, and then now, okay, cool. Okay, this touched one of the questions that was asked me the other day, yesterday. Then the other thing that where we got yesterday, we got to write something like the change in theta is equal to some forcing term, right? And I showed to you what this expression of this forcing term here is. Okay, and this can be used to build some optimization routine, but unfortunately, it in many cases doesn't converge very well. Okay, and then something that turns out that works, improves the performance significantly, is to add the geometric tensor here, which is and this technique is called stochastic reconfiguration. Which, as I mentioned yesterday, was put forward in many years ago on Monte Carlo studies by Sandro Sorella. Reconfiguration. Okay, so what is this geometric tensor? Okay, and I will probably show you how to derive this from time evolution. So you can think of it as some kind of time evolution imaginary time. Okay, but for now I will just give you the result. Okay, so and use that to discuss various things. So this is the d theta that we discussed the other day. Okay, so let's say theta p. Okay, star minus expectation value. Okay. Okay, and then of course is expectation value over all this thing. Notation is not great, but I will still use this notation here. Okay, and this would be S PQ. So what is this matrix? Okay, it's known as geometric tensor and maybe other names as well. Okay, and it's a, if you look at it, is a NP times NP matrix. Okay? So, if you end up having 100,000 parameters in neural network, it will be a 100,000 by 100,000 matrix, okay? And what you will have to do is to take the inverse of this, right? So So you'll have del theta.
What is the D here?
Sorry?
D.
It's the variation of theta, right?
No, D. Capital D. Capital D.
Ah, yes. I defined it yesterday. Let me remind you. D theta. Okay. Partial ln of psi of the for a certain configuration x. P theta P. Okay? Yeah. Okay, so you'll have to take the inverse of this. Okay.
What is the dot of that? The time derivative?
Dot?
C theta P dot, that is star. Oh, star.
Star, conjugate. Yes?
And is delta theta equals to A. That's equations actually. What actually equals to D. Is delta theta equals to A. First equation is equals to
Yes. So you want to find delta theta. You want to see how, you want to optimize theta, right? So you want to do theta at a certain iteration plus 1 is equal to theta iteration n minus some rate and then del theta. Okay? And so this del theta would be s minus 1 f, right? And each one is computed, you need to estimate it with some Monte Carlo techniques, right? You need to sample and take these averages. Okay, so now there are some difficulties with this object here, okay? Because first of all, if for really large network you need to inverse very large metrics, okay? And then it's noisy, okay? And it could have some very small singular values. Okay, so that this can become very difficult. So, like in many things in machine learning, what you can do is you can regularize it. Okay, and one way to regularize S is to say instead of S regularized, okay, let's call it SR, equals to S plus some lambda identity. Okay, that's one way. Another way is to add extra diagonal elements. The diagonal elements increase the value of the diagonal elements. But this is a very nice approach. You put some small values here and regularize the matrix. Okay. That's one approach. And this is actually highly recommended. You don't regularize it. It would be very, very hard for you to reach ground state. In a relatively recent paper by Gravina and Vicentini, they also look at how you may want to vary this as you optimize so that you have a good values for lambdas. They were looking at time evolution, but it's similar.
What does this regularizing do?
So it makes the metrics much more stable to invert. Okay. Now it will not be exactly S, okay, but you will perform much better. Okay. Now, so this is fine, but there is still the issue that S is very large. Okay, it can be very large. So how to deal with the fact that S is very large? There is one approach that has been used in some works and in chemistry, which is called Kronecker factorization, KFAC, Kronecker factorization, and then which basically divides. Okay, grosso modo, is actually more involved than this, but basically it derives the metrics in different blocks and optimize them block by block. Okay, it's actually a bit more involved than that, but this is kind of like a good idea. Another approach has been developed by our group. We call it sequential local optimization, SLO. sequential local optimization, which relies on, since I'm very biased by DMRG, okay, I was thinking a bit along those lines. And so when we were trying to look at the ground states, for example, for example, an RBM, but this is generic, it can be expanded to many other types of neural networks. And later I will give you a little survey of different types of neural networks that people use. So point here is that you have the inputs of the spin x1, x2 here, x3, x4, and x5. Okay? And what we're looking at is like, okay, the Hamiltonian is local, a lot of interactions are local, and we want to build up the correlations from small to large. So why not we look at a block? Okay, so we look at a block, and then we see all the parameters that are connected to the block, and then we optimize only the parameters that are connected to this block. Okay, and then once I've done that, I move on to the next block. Okay. Now that you have taken my classes on DMG, you see that there's some similarities there. Okay? And then you continue, next block. Okay, and so on and so forth. And you only optimize the parameters. Of course, if the network is deeper, then you can do this different layers, but with the similar ideas. And what we found out is that compared to optimize the full S, this was converging a little bit faster, but more importantly, we were getting much better correlations. So when we're looking at the ground state correlations for ferromagnetic, antiferromagnetic order, and so on, okay, it was a simple model, maybe more harder models, things are not as straightforward, but we were getting correlations that were closer to the exact one compared to at the same value of accuracy in the energy. Okay, so, okay, and if I want to plot this in a similar way to this case, okay, then you can think of it in some kind of a very approximate and quick way that we only optimize on certain blocks, but as we do that, we have overlaps between them, okay, and this seems to be quite helpful. But another method that is super cool was used a lot in Trieste, I think, by the group of Becca. And then there was this nice paper as well by the group of Heil. And it's something known as mean SR, which is useful for when you have a massive number of parameters, such that the number of parameters at each point in time is larger than the number of samples. Okay? And the way it works is that you turn this matrix S, which is n parameters times n parameters, into another matrix. Let's call it, does this make sense? No, it's very ugly. Okay, let's call it like this, okay? Which is, very importantly, number of samples times number of samples, okay? And how does this work? Now you can imagine that if NP is much larger than S, maybe you take, you have like 100,000 samples, sorry, 100,000 parameters and 10,000 samples. So it can be 10,000 more, right? And then you see it's a lot easier. Let me show you how we do it.
What are you constructing?
This S matrix. The S matrix, the geometric tensor that I need to invert, that is made in that way. Okay? So actually, since it's there, the formula, let me do, don't move, let me do it here. And
if the number of parameters are greater than the number of samples,
yes,
how do you expect the algorithms or because you
yeah,
have a lot of parameters?
yes. So each step, okay, you have maybe 10,000 samples, still 100,000 parameters, right? And then you continue. You do this for many epochs, okay? So in the end, you do samples along many samples.
Space are getting changed.
Yes. Okay, if you look at the structure there of S, actually can be written as some X dagger X, okay, where X dagger, or X, let's say. So let's look at it here to be clear. This is NP times NP, and this one is going to be N sample times NP, and this one here is going to be NP times N samples. Okay, and this is actually how you generate these averages, right? So N samples times NP. So X is d theta p, okay, X, okay, minus some expectation value. Okay, and so you can see that you can build this as a matrix. Okay, where you have all the samples this way, okay, and all the parameters this way. You keep different samples this way, different parameters this way. You build this matrix, yeah, whatever it is. Okay, and then computing the expectation value is indeed summing up over all the different samples. Okay, and summing up over the different samples mean you can do this matrix multiplication. Is indeed doing the sum up over all the different samples. So okay, so S can be written in this way, and S regularized is X dagger X plus lambda identity. Okay, good. Then what about yes? You see, I have here I can have many different samples from the X, many different parameters from what I choose to derive from. Okay, so along this line, along this line, I change the different samples, and here I change different parameters. Okay. Cool. The other thing that you may not have noticed, but looking back at yesterday's stuff, you can do the same also for F. F can be written as some X dagger and some FE, okay? Where here you have, because you remember, it looks like this, D star theta X E log X, okay? So yeah, you are actually summing over the different x's, okay? And so you can build it as this matrix here times a vector where you have all the different E-logs.
Please remind what was F earlier?
This one?
F capital.
It's the gradient that we derived yesterday, okay? Okay, so now I need to do S minus 1 times F. S minus 1 means doing X dagger X plus lambda I. Okay. And to be precise, let me write this lambda I as NP times NP. Anyway, so small nobody can see it. I hope you can see it. And then minus 1 times some X dagger F. Okay. And what we're going to show to you, and this is equal to doing x dagger times yes, x dagger plus lambda, a different identity, which is ns times ns to the minus 1 times f. Okay? So you have here this times this, and becomes this times this. Okay? This is really cool. This is true. It's not difficult to prove it. Once you do x dagger, x plus lambda identity, minus 1 times x dagger, and then you say equals to x dagger, x dagger plus lambda identity to the minus 1. What you can do, you can multiply both sides by x, this thing. Oh, how many things did I put? Okay. This thing at the left, and this thing at the right. And it becomes x dagger times x dagger plus lambda identity equals to x dagger x plus lambda identity times x. Okay? Did I do it correctly? A dagger. Okay. And this is obviously true, right? You expand it. You have x dagger, x dagger, x dagger, x dagger, and then you have x dagger, x dagger. Okay? So these beautiful things allow you to invert, once you rotate, okay, to invert not S, but this new meanness, okay, which it can be a lot smaller, okay? So huge savings. Good?
How
Yes?
can you switch this x dagger like from left hand side to right hand side? You have switched the x dagger.
I have not switched. I multiply this side by the inverse of this, right? So I multiply here by x dagger, x plus lambda identity, okay? And I do it also here. Okay? And then I do this the same for this thing. I multiply here by x dagger plus lambda, and I do it here as well, right? Okay? Good. So this is very powerful and can be used for ground states. And then I will show you later when we do time evolution, we also used it for time evolution. And so we could do some tricks there. Okay. Now let's go to time evolution. Ken, questions? No. Okay, good.
This is possible because capital F is x dagger F.
Yes. Yes. Okay.
So F is a NP plus 1 vector, right?
Sorry?
F, small f,
Yeah.
is a NP plus 1 vector, right?
Yes, correct. An S, number of samples that cross one. Because it's ELOC, okay? There is no P there. You don't derive by theta P, right?
But how that is operated, we can the left hand side I can understand this x dagger is NP cross NS.
X dagger is?
NP cross ns. NP by ns.
Yes, NP times ns, and then you multiply by ns times 1, you get NP times 1, right? Which is F. F is NP times 1. Good? Okay, time evolution. 12:15. So I wish I could derive for you, but let me just show you how to we get to describing the time evolution, and I will describe to you two main methods. One is TVMC, time dependent variation of Monte Carlo, and the other one is also known as PTVMC, projective time dependent Monte Carlo. Okay. So let's start from the first one. The first one, you see it in the first paper by Carleo. Okay? And the PRL in 2020 by Schmidt and Heil has a very clear derivation of all the various steps and how they use it. And the principle is this. Let's say you have psi. You know psi at certain time t. Okay? And then you want to evolve it. Okay? So you put maybe, okay, let's say evolution operator. Okay? And now you want to have the new psi, okay, which is not at the time t, but at some time t plus delta t. Okay? So it's a new psi. And what you can try to do is to reduce the distance, so you can compute some and normalize it. Okay, so this is some distance, and then of course you can take maybe the square root, the cosine, and then you get a good Fubini study distance, and then you have a you can minimize this distance. Okay, but let's just look at the essence here, this portion here, because it will be useful also later. Okay, so now what you can do, you can expand u into 1 minus high tau h. Sorry? Survival probability. No, what I'm trying to do, yes, let me try to explain this a bit better. I'm trying to find the equation of motion for theta. Okay? And so what I'm going to do is to write u in this way. Okay? Because in the equation of motion for theta, this will be 1, right? And so it would be maximum.
What is theta at time and t plus d?
T.
Theta at time plus d.
So the idea is that theta would be a function of time, right? And I want to find equations for this theta. And so I know the Schrodinger equation, so I try to translate that into an equation for theta. And the way to do this, one way to do this, is to write u in this way, and then psi for theta t plus del t, you can write it as some 1 plus theta dot, okay, and then you have your d, maybe p, okay, sum of a p, yeah, d theta p, okay, and then psi. Okay? So this is because the derivative of psi for the theta, okay? So you're shifting psi. So once you do this, you get to a final expression, because it's already 12:20, so I'll go to the final expression, which is very similar to the one for the search. for the ground state search, which is S theta dot is equal to minus IF, with the same S and the same F that we had before. Okay? So, and this is actually a way to derive maybe if you do imaginary time evolution, and instead of I tau, you put minus tau, okay? You can derive stochastic reconfiguration in this way. Okay, so this is the time-dependent variation of Monte Carlo. What do you do? At each point in time, you figure out what is F, figure out what is S, and you can maybe use an integration method like Runge-Kutta, okay? Second order or fourth order. And what is it? Fourth order method, let's say if, let's say y dot is equal to F yt. So you want to do y, so you generate a k1, which is equal to f of y t, correct? Then you have a k2, which is f of y plus k1 tau t plus tau over 2, k3 equals to f of y plus k2 tau t plus tau over 2, and then you have k4 equals to f of y plus k3 tau t plus tau, something like this, if I remember correctly. And then psi y of the next step is equal to yn plus k1 plus 2, k2 plus 2, k3 k1 plus 2, k2 plus 2, k3 plus k4 divided by 6, right? So at each point in time, you need to figure out the new gradient, but you have updated your thetas in this way, and so you can follow through, okay? So that you have a very clear way to do this. Of course, you need to be careful because S is, again, can be not very well conditioned, can be noisy, and in the paper by Schmidt and Heil, they look at how to truncate, to do a single value decomposition of S, and truncate some elements about in making sure that you have good signal over noise ratio. Okay, so this is one approach. The other approach, and this approach already was in the first paper. Yes?
In the variational case, the ground state search problem, this
Yeah.
substitution that we had S delta theta, this thing, was an exact one, but here it's an approximation because you take that U to be the first order approximation. E to the power minus I tau h, we have written at identity minus I tau h.
Mm-hmm.
So,
there are in both cases approximation to a certain order, right? Okay, so this is correct. Once you do everything consistently up to second order, you get this expression. Okay.
no, but you have taken.
In the other case, for the ground state search, you also do some approximations, right? Because you're taking.
The equation was exact.
Because you take the gradient and so on. Yes, this is exact up to second order. Yes. When we were taking the gradient, the S didn't come out, right? Okay. If you want to derive with a stochastic reconfiguration, then it will be this case. Okay. Cool. Okay. So the other approach starts for something similar to this. Okay. Something very similar to this. Okay. Yes. There are so many things to say. And instead of deriving an equation of motion for theta, just more, let's say, plainly says, okay, given given a certain psi, okay, what is a new psi? Let's call it, again, we can call it t as delta t. But I just want to optimize these new thetas, okay? I don't want to find the equation of motion. I don't need the delta t to be very small, okay, integrate. I just want, given this, and given some interval delta t, find the new psi theta, okay? And now, it's basically the same formula that we have written here, okay? But let me write it again so that we can do some games over it. Okay, and the idea of this approach is to say this thing here okay, is like an effective Hamiltonian. Correct? It has all, you know, it's Hermitian. Okay, so I can think of this as effective Hamiltonian, and then what I'm trying to do is to optimize this psi over this Hamiltonian. Okay, and try to maximize this loss function. Okay, or if I put 1 minus, then it would be minimize the loss function. Okay, so this is kind of the idea, and it is. Let's do a few steps so you can see some interesting part of it and some differences compared to the other approach. Okay, yes?
In this case, you have to optimize it for each time step, right?
Correct.
But on the other hand, here, like you can have a
Every time steps, you do, once you get the new one, okay, you need to find the new f and new s and do it again, all of these steps, right? Yeah, second order can be sufficient maybe. Actually, there's quite a number of papers just use second order. Okay. What turns out that once you do this approach, you can often allow yourself to use a much larger delta t. Okay? But okay, there are also advantages to use this approach in some cases. And as of last year plus, there are new approaches that maybe I will have a little chance to give you a little hint how they work. Okay, so this effective Hamiltonian, right? Let's write this thing down, okay? You can see this as a sum over, okay, let me call this thing to ease a bit the notation, I call this thing phi, okay? And I call this psi, so that I don't have to carry all these thetas around. It's a little bit lighter. Okay, so I have phi conjugate for a certain x, and then I have u x prime, and then I have psi x prime. Okay, this is the first term, sum of x prime, and then sum of y prime of psi y conjugate u dagger y prime, and then you have psi y, and then normalizations, sum of a z of phi z modulo square, sum of a z prime. Thank you. Phi psi z prime modulo square. Okay? And here you can see that you can write You can build these E-logs and probabilities we were doing before. Because what I can do, for example, is to bring this inside here and build some E-log. Build this inside here and build some E-log as well. And so I can write the sum over x of p over the probability phi, okay, of x times some u log of x. Okay, so this is what comes from the red part. And then from the blue, I have a sum of a y of p over the probability psi of y and some u dagger log, okay, of y. Okay? So you bring it inside here, then you do the same trick, you multiply and divide. Okay, I multiply by phi of x, divide by phi of x. I get E log. This portion here would be E log. Okay, U log. And here I get the probability from this over this. And similarly here, I can multiply and divide by psi of y, okay? And then you get the other U dagger log, okay? And you need to be careful of what is above and what is below, so maybe you can write it in notation, it's psi phi, and here in notation will be phi psi, or up to you, what notation you want to use. But as long as you consider. But this is, if you look at it, it's actually quite interesting, because basically you are sampling from the initial distribution at time t, and you say, okay, I want to get this evolution in one direction, but also sampling from the other one, I want to do the evolution in the other direction. Okay, it's a nice way to look at it, and of course you can also write it in other way. Now there is a big problem here, though. Who can catch a big problem? I kind of hinted it yesterday. The big problem. It's no, you never have this issue, and because you sample from this probability, since I sample from there, definitely is not zero. Okay, so that is not a problem. We would have had this problem also yesterday, but we didn't mention this problem. The problem is this thing here. It's no longer sparse. Okay, it's in generally dense. So what to do? Well, we've seen some solutions for this. For example, you trotterize it. Okay, you do first a small one, and then you trotterize, similar as you did as you were doing for DMFG or other problems. Okay, you can do the evolution on a pair, and then another pair, and then another pair, and then you come back. Okay, this one you do it twice. Okay, so for example, in 1D, 2D is a little bit more a little bit trickier. Okay, in fact, it's kind of heavy to do this on 2D because you will have to do maybe these pairs. Then you have these pairs. Okay, within each color, they don't commute, but different colors. No, within each color they commute, but within different colors they do not commute, right? And then you have these pairs, okay? And so on and so forth, right? So you can get very involved. But there is other approaches developed for ground state search. No, also for time evolution. Yes, beautiful approaches that both for ground state search and time evolution, developed by Nice and Carleo, then used also by Gravina, Vicentini, where instead of write U as maybe 1 minus I h dt minus h squared dt square over 2 and so on and so forth, right? This is also could be another approach, right? You can do to second order. H square is also sparse, okay? Yes?
Most of the time H is sparse matrix, so why U is not that sparse?
The exponential of H is not sparse. Try to do it, it's obvious.
But you actually linearize the U from
No, this was when I derived TVMC. Okay, but here I don't want to. I want to use a big fat U. Okay, that can do large delta T. Okay. So of course you can say I can do Taylor expansion. H square actually is a bit cumbersome to do it, but this is not really accurate. I mean, it doesn't work very well. So what they suggest instead is to do a product, let's say over I, no, let's go L, of 1 plus ALH. Okay, maybe I put delta T here so that A does not depend. Okay, and I can do many of them. And if you choose A well enough, you can get to second order, third order methods. You can do 3 products of this. Each time is very sparse. Okay, so you do the evolution with one, and then with the other, and then with the other. Each time is very sparse. And after you've done 3, you get your nice U, maybe a third order, or you do 4, you get U a fourth order. Okay, so this is a very nice method that yeah, I think Nice and then more recently Gravina and others have used in the calculations. Okay, so good. These have been until December 2024, the only main 2 approaches, big general approaches. And then I think December 2026, there were 2 archive papers on the same day by Van der Broek, Schmidt, Annabel Bohr on one side, and Sinibaldi, Giuseppe Carleo on the other side. And they used a very different approach. After that, there has been another work in a similar but quite different way of thinking by our group, and then also from a group in China doing chemistry simulations. And the idea, is the main idea that is common to all of these works is that instead of okay, so let's suppose you know that theta is changing in some way over time, some theta p, okay? Instead of each time figure out what will be the next, okay, and try to do something. The idea is to, okay, let's find some loss function that optimizes over a range and figure out what will be this function over the full range. And this, I think, is the idea that is common to all of these 4 works that I mentioned. And then how it is implemented differs from different groups. One, maybe easier to explain approach is the one by the Van der Broek paper, where they use a neural network, specifically a transformer, and as inputs you have your x, your configuration, but also the input time, okay, as a variable. And so that the network has some time dependence in itself. And then the loss function, it's basically TVMC okay, at different times. Let's say tk, okay, so everything is function of time, tk, okay, and then they sum over the different times, okay. So you are optimizing this transformer or this general neural network over all the times in a certain region. And then, of course, then is able to get the derivatives, and then you need to see how to join different intervals and so on and so forth. So that was a nice approach. The paper by Carleo is called Galerkin neural networks. So, and then use a sum of many RBMs at different times and then connects them. And our work, since we know that theta is a function of time, we write it as some sum over, let's say for each theta p is a function of time, sum over some other parameters k, let's say, of some capital theta pk, and then some basic functions of time. So the only time dependence is in this basic function here, and then I try to optimize over a certain period for these time independent parameters. Okay, so the works by Van der Broek and et al. And Sinibaldi et al. Is fantastic. They simulate a very large 2D system, which is really the frontier, because when you want to simulate 1D, still I think DMRG rocks, and it's hard to beat. But when you go to 2D already, DMRG even from ground state staggered significantly. And this, at the moment, for the best of my knowledge, our best hope to try to do time-dependent simulations in 2D in general. And these two works that I mentioned before, they did simulations 8 by 8, maybe even 10 by 10 spin over long times. And the beautiful thing is that when you get you train the object, whether it's the Galerkin neural network or the transformer neural network, over a certain time, you can also ask the neural network to predict what will happen later times. Okay? And you can, although you optimize it over a certain period, it can be quite accurate also at later periods. And this is quite nice. It can help you too. And it's something that also we could see in our approach, and we could use it to better update or initialize our neural networks. Okay, so this is roughly what I wanted to say for time evolution. Now, I talked a lot about neural networks, but I didn't even show you a single neural network, right? So maybe it's time that I talked about a few, and I think the last 15 minutes is maybe for the last 10 minutes and then some minutes for questions. So let me describe to you a few of the most common neural networks that people use.
Could you please write the names of the people you did mention?
Oh, yes. Okay. Van der Broek. I think it's spelled like this, etc. Bar. Schmidt is inside here also. Schmidt. This is December. On the archive, you'll find in December 2024. Okay, this one paper. I forgot what the title is. The other paper, the title clearly as Galerkin neural network. Something like this. And the first author is Sinibaldi. The last author is Carleo. Same day, December 2024. Vicentini is also an author of this. I think. I'm quite sure. Actually, I'm not. I should check. But Vicentini has done also a lot of very nice works in time evolution. Yes. And then, if you're interested also in our work, the first author is Dingzhou Wang. and you know my name. And that was 2025, I think June or July. Okay? And I think it's called a smooth neural network or continuous, something like this. Okay, cool. Yeah, I think Vicentini is not. Okay, so I want to talk to you about neural networks, what different types. Okay, so we have the first one that's been used, and it was the most popular for the first years. Everybody was doing a lot of things. This is the RBM, restricted box machines. And you know, now it's super famous because they also won a Nobel Prize for building up this this network. And it has a visible layer, and a hidden layer. And they're connected. The thing that makes it restricted is that within the visible or within the hidden layers, the different nodes are not directly connected. Okay? So they're only connected through the hidden layers. So this thing talks to all the hidden layers, but doesn't talk to any of the visible ones. And vice versa, any of the hidden layers talks to all the visible ones, but to none of the hidden layers. Okay, this reduces, I guess, the expressive power, but it makes it training so much easier. And in fact, if this is real and you're really representing probabilities, you can also have a more efficient way to sample, something called Gibbs sampling. Okay. Now, the function that describes this is an exponential, okay? And then you sum over the visible layers, let's say I of, you say AI xi, plus you sum of the hidden layers, let's say j, bj, hj. And then you sum over all I and j, okay, and you get h j w j I x I, okay. So this represents everything. Or then you trace out, you sum over all the possible h I, okay. So equals to plus or minus 1. So you trace out the hidden layer. And this is your function. And it actually looks like this, exponential, sum of I of AI xi, then product of a j of 2 cosh, okay, cosh is hyperbolic cosine, b sum of I wji xi plus bj. Okay, so this is what it looks like, and it's actually surprisingly pretty powerful, and with a hidden layer that is about 3 to 5 times the size of the visible layer, you can get pretty good stuff, okay, in many cases. Even for time evolution, for some problems, we just, you know, and hit the layer there's like 5 to 7 times the visible one, you can get pretty good results. Okay, and the other thing that is beautiful about this is that you can compute all the gradients analytically. Okay, you can see if I take the derivative of f over the AI, okay, yes, it's just xi. So let's say, for example, I compute D AI. This is just xi. Okay, and then you can compute the derivative of bj. This would be the tangent, hyperbolic tangent of sum of I of wji xi plus bj. Okay, and if you do d of omega ij, this is again the tangent of sum of I, let's say I prime, omega j I prime x I prime plus bj, and then multiply by xi. So we have all the derivatives analytically, and then you can build up everything. Okay, so that's fine. Problem is that, okay, it's not so expressive. You want to, yes?
So I don't know about the functions. So F means activation functions.
No. This is F is really the full network. The full network is this thing.
So one question, H is the, I think, hidden layers.
Yes, the parameter of the hidden layer. So the value of the hidden layer, which could be +1 or -1. Like the visible layer can be +1 or -1. The hidden layer can be +1 or -1.
So there should be another sum on X, which is can be +1 or -1.
There is a sum. No, this is F for a certain X. Okay, so maybe, sorry. F for a certain X. Okay, cool. Thank you. Yes?
Is it
Similar
similar to the dropout method?
to?
Dropout method, when you turn out some neurons.
I cannot understand.
There is a method which optimizes the neural network by turning off the neurons for some time during the training. So is it similar to that?
No, I don't think so. The whole neural network is this. Okay, now I'm trying to describe to you, maybe I give you another example. Let's say I look at feed-forward neural network, FF and NN, okay? This is, you have a visible layer here, then maybe you have different hidden layers, and then you have an output, okay? Now what do you do? At each layer equals to some function, okay, let's put it, let's call it G, okay, of some weights that act on the previous layer, and then some bias, okay, and this maybe I can call it G of N if I'm doing this at the layer N, okay, so you put an input, you generate the next one, then you generate the next one, and then at the end you can pull it together. Okay, to give some output. This is okay, but has various issues. To have a certain expressive power, you may need many layers. Okay, and then when you train it, you can go into these problems called vanishing or exploding gradients. Okay, so they can be, the deeper they are, they can be much harder to train. And there are tricks to try to improve that. Things called skip net. So you skip some links or you normalize and so on and so forth. But something that came after that.
And what are the D's?
What are the what?
Capital D's.
Capital.
Fast one. Capital D.
Like DAI,
DAI,
Ah, the derivative. It's the same D that I did before to compute the use in a network to build S, to build all the things, right? The derivative of the neural network. Let me. Again, d theta p of certain sample x is derivative of the ln of psi for that sample, so the argument. Okay. Okay, so this is a. Then basically you can build on whatever neural network. There is a recurrent neural network, and these are This was really fashionable before transformers came to life, right? And here you put in some input at different points, but there is really a directionality in how things are going, and then you can have output here. And you can build, for example, an autoregressive network in this way. That's why it was used a lot in natural language processing. It has some, and you can build more over this, but you can see that it's kind of like similar to a tensor network in the idea. And I think also it speaks about some limitation of expressive power that these things have, because you only carry this kind of information. But you can build like bidirectional recurrent neural networks and so on and so forth. So these are quite being investigated. And then you can look at convolutional. Sorry, maybe I should say this is recurrent and convolutional neural networks. In these ones, it's really the next step from feed-forward neural network. Instead of having given a certain visible layer, you use some filter, let's say, or some kernel, which you apply and shift. So you apply this kernel over different portion of the system, and then you get this information, you carry forward, and you do some max pooling or average pooling, you get some information to bring it up. And every layer, you have a filter that goes through the system, get some information and carry out, and you have different filters, and all of this information you bring it forward. So, and you can, and actually you use a lot less parameters than if you forward neural network. You can implement periodic boundary conditions very easily, and there are also very nice advantages. But the thing that came out, the thing that changed the world, I would say, are transformer, right? Change the world, at least the world we live in, is also changing a bit more the world of physics, transformers. In general, these are autoregressive, but you don't need to the autoregressive properties, and you can get them to build just a wave function at the end. So, how do transformer work? Okay, so you have an input, and then you from this you build something that's called attention. And to build the attention, basically it's something that look at the whole system, and uses three elements. One is called key, one is called query, and one is called value. Okay, and bring it together into an nonlinear function. And the idea is really to, for each point, figure out what other points are relevant. Okay, and it's try to learn this through the key, the point, the query, the question, and then the value that it has to give. Okay, and then it brings it up. And this, and you do this for many layers. You do one layer, then you bring some feed forward and bring it forward, and then you do this for many layers, you repeat, then there is some normalization, there is a lot of other things to try to mitigate potential problems. But at the end of the day, you can put here some convolutional layer or some complex layer and spit out, for example, your psi for the initial configuration that you put in. Okay? So this is, in general, what you need is something that can look around, okay, and try to figure out what could be a good psi of x. And this transformer seems to work very well, but in general, you need a lot of parameters for them to work quite well. And in the last layers, you can put in symmetries, you can put other things. There are beautiful works by Becker and others where they get really good ground states using visual transformers. So yeah, 1259. So I guess I kind of rushed through these things. You could spend days talking about these things, but you have an idea of what the different types of neural networks are there and what people are using. And yeah, of course, you can include symmetries. If you set up a symmetries, you can build the neural network such that the symmetries are already taken into account. Some are very easy, like Z2 symmetry is very easy to implement. Number conservation also very easy. You can sample just things in the correct sector. So translation also can implement, and so on and so forth. Yeah, okay. So 1 o'clock. Any questions? You have a question? No? Okay. Yes?
These neural networks will program in connection is one layer between the nodes, right? That's what specifically.
Which network? Only in the RBM.
Yeah.
In the others, no, within the layer itself, no, but the first layer can take all the inputs and build up something, yeah. Or you can take just a portion of the lower layer and build up something, and then shift. You get different outputs and put them together, okay? Yes. But you don't have so my point is that if you look at the RBM, you don't have terms like xi, xj, okay? You only have xi, hj, okay? And you also don't have terms hi, hj, okay? That's the key.
Any other questions? If not, let's thank the speaker for this beautiful lecture.